So hello everyone, my name is Arun Sharma and I am the presenter of this session today. Today's topic is significance of U-beam sections for splice girder bridges. Midas holds the copyright to the material shared in this presentation. However, we would like to thank Summit Engineering, Florida Department of Transportation for sharing some information with us that really helped us in preparing this session and putting it together. The learning objective for today's session are first the U-beam section utilities and advantages for splice girder bridges, the tools useful for generation of U-beam sections in 2 parts and 3 parts. What are 2 parts and 3 parts we'll cover in detail as we proceed. Then the numerical modeling of splice girder bridge using the section, and the construction stage analysis of the splice girder bridge to obtain the design forces. So the session today is divided into 3 parts. The first part is the U-beam section, where we'll be talking about some project applications where this type of section has been used. Then we'll go into the basic definition of this section, that what is this section, what are its various forms, and then we'll be talking about why this section became so important and useful for this type of bridges. The second part would be meeting the analysis challenges. So there are different challenges in realizing this bridge using this section. So we'll be talking about how we can meet those challenges. We'll be touching upon 4 prime topics, that is the section properties, determining the composite behavior of the section, understanding the pre-tensioning and post-tensioning losses, and finally the construction staging of this bridge. The third part of this presentation will cover the demonstration, where I'll be going into one of the popular tools for this type of bridge analysis, and there I'll be talking about the different features that are there that can be useful for this type of project. So there I'll be talking about how you can define these special sections, how you can simulate the temporary supports in this for these types of splice girder bridges, how you can determine and apply the composite action, and then finally we'll be talking about some results that you can extract after the analysis. Alright, so let's begin with the first chapter, that is a U-beam section. So let's quickly look at some project applications where this type of section has been successfully used. So this is one of the projects. As you can see, it is a curved splice girder bridge. It's a twin system. There are 2 U-beam sections used for this project. Similar is the another ramp project. You can see it is also along a curved profile, and it has been supported by shoring right here. So we'll be discussing what is the role of the shoring and how we can simulate it. So I'll be going into more details at a later point. Then another project, here you can see there is you can also consider haunch in these types of sections. So the sections are very flexible, and you can because it's concrete, you can cast in different forms using different formworks and consider different cross sections. So now what I'll do is go into the software and try to show you these projects that are so real in the field. When you create a model, how do they look under an analysis environment. So this is a sample project, as you can see. Now if I press down the control button from the keyboard and hold down the wheel mouse button, I can rotate the structure like this, and you can see this is a straight bridge with 3 U-beam sections, and you can see the bridge has a nice haunch. As you can see, the sections are tapered along the length, and the substructure is also intact. Now this is how the project looks like before it goes out into the field, and let's see different aspects of this particular bridge. So the bridge is the key essence for this type of splice girder project is its construction staging. So here we can see we have started with just the substructure. You can see the hammerhead piers here. Then we'll have the U-tub sections there without any cover, just the bare girders. And if you see right here, you can see the splice gap there. So the members are yet to be applied. So these girders, even though you cannot see the shoring here, it's a very popular method of using point supports at these locations. So if I turn on the supports, you can see there are some sort of supports applied at the splice location. So these point supports represent the shoring for you. So this is the part of analysis where you are more interested in the superstructure design rather than getting the forces in the shoring. If you want to get the forces in the shoring, you can model members underneath it to represent them. Let me undisplay it. Then so we have erected the beams here. Then we will pour the lid on top of it. So sorry, in this stage we'll apply the splice form here. Then we'll apply the post tensioning. So since these are precast members, I would like to draw your attention towards the strands layout and definition. So if I just right click and say display, you can see there are post tensioning strands in the section. But if I go to the previous stage where the girders are erected, you can see they are pre-stressing strands at the bottom of the slab. So if I go to the elevation view, you can see the pre-stressing strands are applied, and then when the splice forms are placed, you can see the post-tensioning strands are applied in continuity. And then we will pour the lid on top. Let me undisplay the profiles. So now the temporary supports are released and the deck is cast on top of it. So you can simulate this type of construction method in your for these types of projects. So now let's move on to the definition of this section, that what are these sections like. So if you can see, we as we mentioned, it is a U beam or a U girder. You can see it is a wide section. So essentially it is a box section without the slab or the lid on top. And as you can see, different DOTs are giving different specifications for the type of sections that should be used in their states. So you can see some standard definitions for the sections. These beams are called U-beam, U72, U64, U96, and all these different configurations are available. So they are the typical girder sections that you can start with. And this is a typical cross section that you are looking at for a two girder system. So this particular section comprises of 3 parts. You can see this is the U-beam. Then there is a lid slab on top of it, which is cast at a later date. And then we have the deck slab on it. Now the reason why the lid slab is there is primarily to provide the torsional rigidity to the structure. Now if you are modeling the bridge along a curvature, there is a lot of torsion in the system near the interior supports. So in those areas we need to provide this kind of lid slab on top so that it can hold the sections intact there and take and increase the stiffness for against torsion. And then we have the final pour, which is the deck slab on top. So like I mentioned, this section has three parts: U-beam, lid slab, and deck slab. And this three-part section is found near the interior supports for the curved bridges, whereas the other part of the span will just have the U-beam and the deck slab. So there will not be the lid slab every time. And if you look at the reinforcement details here for connecting these U-beam, lid slab, and the deck slab, this is how the composite action is achieved. So we have some stirrups that are coming out. We have to provide some detailing. So when we pour the concrete, we can have composite action in three stages: first with the lid slab, and then with the deck slab on top. So when you're simulating this in an analysis environment, you have to make sure that you're able to capture these composite section behavior. So going further in the definition, for quite some time engineers have developed this practice that concrete bridges are always straight, or they could be curved when they are constructed in segments, and the segment lengths are very limited. Most popular type of construction methodology that resembles what I'm talking about here is balanced cantilever construction, where the segments are shorter in length and they are along a curvature, and then the engineers erect one segment after another. But this section has somewhat revolutionized how the splice girders could be modeled. So this is a casting bed, and this is a curved casting bed. So you can create a curved U-beam girder here, and this is how the reinforcement details can be provided. You can see the ducts for the placement of the tendons, and then this is the completed segment. So here the segment lengths are longer than the conventional segmental construction methodology. And then once these segments are cast, they are lifted and placed onto the bridge. And this is a very important part of construction, as the segment lengths, as they get longer and longer, they become heavier, and these segments are very heavy and they require special or heavy cranes to lift them. So in some cases it has been also seen, at some sites there have been some tragic accidents where the cranes have failed to lift a section because they were not properly supported at correct intervals. So just that you have to be a little more accurate, a little more cautious when you are dealing with these types of bridges and you are lifting them. There are different types of sections. This is the conventional segment, and this is one with the diaphragm. So they are applied at different locations. As you can see, this has some sort of lid support here, where the lid will be poured at a later point. And this is how the overall bridge layout looks like. So if you're working on a curved bridge, so this is a standard practice that is presented by the DOTs, and it is adopted by different consulting companies. So you can see the span 1, span 2, span 3 is a 3-span bridge, and the length ratios. If the span 2 is length L, then the span 1 and span 3 are kept somewhere around 70% of that span. And the entire bridge is erected in 1, 2, 3, 4, 5 segments, and it has splice 1, 2, 3, and 4. and underneath every splice there are temporary supports that needs to be applied. So this is somewhat in line with the accelerated bridge construction practices, where you can cast these segments along the curvature, lift them up, put it here in the zone where it is supported over the piers. In these zones you have to apply the lid slab on top to cover the U-girder opening and provide enough stiffness to the section to avoid any kind of torsion in the segment and give it its stability. Because after this stage we will be doing the post tensioning and applying the deck slab on top of it. So let's talk about the advantages of using this type of section over other conventional practices. So let's first talk about eye girders, which are a very common practice. So as you can see in this cross section, there are 1, 2, 3, 4, 5, 6, 7 eye girders, and for this width of or this wide cross section, if you're using a U-tub section, you can have 1, 2, 3, 4 girders only. So as you can directly see from here, this type of section reduces the number of line girders, and that means the entire cross section will be much more stable. It will not be very flexible, and therefore it is much more easier to handle and erect for longer spans. So therefore it enables you to get lesser girder lines and therefore a stable cross section. Then it can be used for curved bridges as well as for straight bridges. Like I mentioned earlier in the presentation, that all this time engineers think that, or have developed this practice, that every time we are talking about concrete, we will be considering it for curved bridges only. So this section is very efficient for handling both type of girder arrangements. It could be curved, it could be straight, and the sections are pretty flexible. And that is the biggest advantage we can get out of concrete, is that we can cast it in different forms. So if you are varying your span lengths and you would like to go for a tapered section from center of the bridge to the pier support, you can very well get that kind of configuration. And if you are doing the design check and you are planning to optimize the weight of the structure, then you can consider different alternates also. So based on the type of bridge you are doing, different span lengths and all, you can come up with a more optimal section rather than just being limited with the conventional eye section that we are using. And last but not, the second last reason is it is aesthetically appeasing bridge. So it looks really beautiful as compared to the conventional eye girder bridges. So these are some of the reasons why engineers and DOTs and consultants and contractors are inclining towards this type of section. And whenever we talk about curved girder bridges, we always consider it to be a steel structure. So let's see how does this type of concrete splice girder bridge compare to a steel girder, a curved steel girder bridge. So this is a cost comparison. We are not disclosing the project from which it has been taken, but we are thankful for Summit Engineering to share these kind of brief details that will help us in understanding how efficient these sections could be. So as you can see here, as compared to steel option, the girder cost is much economical because concrete any day is cheaper than steel. The second thing, if you compare, is the erection cost, and steel always has a higher erection cost as compared to precast girders. Then false work. Agreed, steel requires less false work because you don't have to cast any part of the steel girder, whereas curved precast girders require false work quite often. And post-tensioning, steel doesn't need any post-tensioning, whereas curved precast girder needs post-tension. So even if you add or take everything into account, add everything up, you will still see curved precast girders are much economical as compared to their next best option, which is steel. And for several years, this has been quite close when we talk about curved steel option and precast U-girders, and these types of case studies and evidences that have come up has definitely favored towards splice U-girder bridges. So that wraps up our first chapter, where we were trying to give you a brief idea about what is this section, where it has been used, and more importantly, why this section has been used by different companies and different DOTs. So let's move on to chapter 2. Here we'll be going into the analysis challenges of these types of bridges. So the challenges could be categorized under two main headings. There are some field challenges, there are some analysis challenges. For field challenges, if you see, like I mentioned, the segments are very heavy, so they require heavy cranes. Then you always require temporary supports, and for this you require show rings during the construction work. Then since their construction is pretty complex, so they require complex phase construction, and for which you really need to have an expertise in this field and erection engineering. So not everyone can just start or work on this type of project. You have to have a decent amount of experience on these types of projects. You should have either been in one of the teams who have done this type of work, or been on the field in some or the other fashion. So you definitely have to have some prior experience for working with these types of bridge sections. Then the another category is analysis challenges, and this is what we'll be focusing upon in this part of the presentation. That since these sections are of various sizes and dimensions, so the section property computation is pretty critical, and not always it is very easy and straightforward to get the entire cross-section behavior, because there are multiple parts in this cross-section. Then capturing the composite action. Again, like this one section is constructed in 3 different steps, and there will be a time where the girder will be by itself, then there will be girder and the lid on top, so that will behave as one section, and then after some time there will be a third part added to this section. So you have to capture the behavior of the entire cross section in different stages. Then tendon losses, because they are precast sections which are pre-tension and who are post-tension. So there are elastic deformation that you have to consider. You have to consider other types of losses that will occur in the tendons. So that is a critical part of the analysis here. And then obtaining forces and camber deformations, and monitoring or capturing time-dependent behavior of the concrete. All these put together create a big analysis problem for the engineer. So like I said, you have to compute the cross-section properties, and since their shapes are different, you need to have some sort of calculation procedure that can accommodate these kinds of sections. And many times engineers resort to different types of spreadsheets for considering uh, uh, the uh, the section properties and computing them, or sometimes they are not that lucky and they use just hand calculations to get there. And whereas some companies or engineers prefer using some efficient tools that could be useful to make their work process much more smoother. So we have a tool that will be quite useful for handling these types of sections, that can bring in your drawings from of these sections into your analysis environment, and then you can divide that into 3 parts and apply different material properties and compute their section property in no time. So this tool is called Section Property Calculator. We'll go into its detail at a later point. Then the second challenge was capturing the composite behavior of the section. So like I said, in the first construction stage, let's say it is just the U-girder. In the second, it is U-girder plus the lid on top. And the third or the fourth construction stage, depending upon your construction sequence and post-tensioning of the structure, you can have different construction stage. It could be third, fourth, or fifth. And at that point, when you have poured the deck on top, the structure will become a composite section. So you must consider this composite behavior, and for that engineers face even more challenges, and many times the girder material and the lid material and the deck material are not same. As you can see in this example here, the part 1 material is C9000, and part 2, which is the lid and the deck, have C4500 grade of concrete. And since these members are cast and are poured at different ages, different maturity of the concrete, you have to capture the age effect of the concrete here, the creep and shrinkage that is occurring in the concrete. So those types of time-dependent effects are needed to be accounted for. Then this is a screenshot from the previous example that I showed you. We have precast girders that have where the precessing strands have undergone some sort of losses. Then we place the splice member or the pour, and then we do the post-tensioning through it. So the entire system changes from a simply supported system to a continuous structure, and that causes differences in deformation, in losses, in total structural behavior. And the most important effect that comes in is the secondary effects of the post-tensioning. And as we know, as AASHTO also asks you to use the secondary effects for designing these sections, you must account for the primary and secondary effects separately. So this is another thing that you have to pay attention to. So I'll go a little more in depth for the pre-tension and post-tension losses. As you can see, this is a table where you have different column heads, and these columns you can see some values for one of the tendons at a given construction stage. So let me quickly explain to you what are these losses that you need to consider. So to start with, we have to consider the stresses after immediate losses. So here the losses that are what we mean by after immediate losses, the instantaneous losses that occur. So depending upon the type of pre-tension you are applying, whether it is pre-tension or it is post-tension, there will be different types of losses. So it is sometimes really hard for any software program or for engineers to consider these losses separately. What they do is either they just lose the track that it was a pre-tension tendon strand, and they apply and they compute the post-tension tendon losses. So there's a lot of scope of human error that keeps all the engineers on their heels. So in post-tension beams, as we all know, there are friction losses and credit losses that make up the instantaneous loss. So if it is a post-tension beam, we will see under stresses after immediate loss, the instantaneous losses to be comprised of friction and anchorage losses. And if it is a pre-tension beam, you will see the elastic shortening loss, which occurs right after the release of the strands. And the formulas are pretty simple and straightforward, and these are the formulas that are applied by any tool for computing the losses. So these are the anchorage loss and the friction loss. Then elastic deformation loss. Now this is something that forces an engineer to look into a numerical model, because assessing these through hand calculations is not that easy. What happens is, if you have two set of tendons, let's say these are just the tendon ducts, and then we are post-tensioning it. So first we post-tension tendon 1. So this will deform the cross-section, so the cross-section properties have changed. And then we'll be precessing the second tendon. This will cause reduction in the size of the section, but as well as it will affect the stresses in the adjacent tendons. So you must account for these types of elastic deformation, because in splice girder bridges, this is a phenomena that will definitely occur as you are post-tensioning a pre-stress section, and you have to account for all these other effects. Then creep and shrinkage loss. This is highly dependent upon the code and the practices that you are applying to assess the material behavior. If you are using AASHTO, ACI standards, or CBFIP, depending upon that, there are different formulae. That information will be too much of elaboration, so I have skipped that information here. We can definitely discuss about this particular aspect in more detail at a later time. And then finally, the relaxation losses. This is the relaxation in the tendons that will occur over time. So you can, as you can see, this one of the definitions as given in CBFIP is that there are different factors involved that that should be considered at different time steps. So this is not something that that is pretty simple, straightforward. You put in the formula and get it. You have to check this stress or the loss at different time intervals. So this is a time sensitive loss that you should account for. So all these losses are very essential for any pre-stress concrete analysis. Then let's move on to the fourth challenge, which is the construction staging itself. As you can see, all these bridges are heavily supported on their shoring, and depending upon the road alignment underneath it, you can either have just nice support right under the bridge, or you can use for go for bend caps and then provide shoring. So what are the challenges that engineers have to go through in this? First of all, the splice joints, their deformations and the camber, that is very critical to ensure the final layout of the bridge. So you have to model those support at appropriate locations, and sometimes you have to assess the forces that are coming in the shoring member. So you would have to, instead of just applying a point support and getting the camber value for the superstructure, you would have to model the entire system underneath it, something like this, and then assess the forces. So if you look at the standard construction staging scheme as presented by major DOTs, is as shown here. So it is the same bridge that we were talking about in the layout. It is a 3-span bridge. First stage, you should have your abutments, pier, or interior supports, and the shorings in place. Then you place your segments 1, 2, 3, 4, 5 like this, and then you place the splice member and do the post tensioning, and then remove the formwork, which is a standard practice. So you have to simulate all these in a numerical environment because these are important. You have to see as what will happen with the changing the age of the structure, what will happen to the losses in the tendons, what will happen when you remove these temporary supports, how much deflection will it bring in. So all these things are very significant for splice girder bridges. So this is a simple simulation of the one of the curved U-shaped beam bridges. You can see these are number of temporary supports, and these are the main piers. So you can see the first stage, you will just have the interior supports and the shoring members in place. Then the second stage, you will have the girders erected. Then the third stage, you will pour the lid on top and do the post tensioning, and then you will activate or apply or the deck on top and remove the formwork. So this type of construction staging needs to be simulated. So this brings us to the final chapter of this presentation, where we will be talking about the section definition. It's more of a demonstration. So what I'll do is show you how these sections are generated in real time. Then in construction staging, how are the temporary supports applied and removed, and how to simulate the composite section, and then finally the result interpretation. So this is a simple bridge that I have modeled for you guys today. We are just focusing on the superstructure behavior, so in this model we will not be modeling or analyzing anything to do with piers or the shoring members. What we'll be doing instead is that we'll be applying the supports at the given location and understanding the behavior of the superstructure. So this bridge will have 3 spans and 4 splice connections, and it will be a twin girder arrangement, as you can see. And this is the layout for the demo that I'll be going through today. So I'll start with the section definition and then assign that section to the geometry of the bridge. Then I'll be defining the time-dependent material behavior for this particular bridge. Once that is done, I'll open a new file where I'll be focusing upon how you can activate and remove the temporary supports for your numerical model. And then I'll be talking about how you can simulate the composite action for this type of section. And then finally, I'll be using the completed analyzed file to go into its results. For the construction staging, we'll be following this given scheme here. We'll have the stage 1, where we are activating the abutments and the girders, the main girders, in one go, because we are not modeling the substructure, so I didn't make 2 different stages. You can go for first stage to be just substructure, the second stage to be the superstructure added, but since that part is missing, we just moved on with the superstructure. In this stage, we'll be having the girders erected with an age of 28 days. So actually the girders have been in the casting yard for and attained maturity of 28 days, and then brought to the site. And when they are brought to the site, they will have the following supports applied. They will have abutments, they will have bearings, they will have temporary supports. So these beam and releases, temporary and links are temporary, and beam and releases are the temporary supports. Links are to simulate the eccentric behavior, because the supports are not directly applied at the centroid location. They are applied at the bottom of the U girders. So we'll be using links to simulate that, and then for modeling the bearing or the interior supports, we can use some type of elastic links, or directly a point support with some degree of translation allowed. Then in the first stage, since we are not adding any external load, it will be just the dead weight of the structure erected so far, so we will be considering its self weight. And then in stage 2, which will be just have created it for 1 day. Actually, in this stage, what we can consider in the field is that once this girder is erected, we'll be pouring the lid on top of it. We'll let it stay for 14 days, and then we'll analyze it in stage 2 on first day with the lid that is activated with the age of 14 days. Then in the following stage, we'll be doing the post-tensioning. So therefore you can see the load there. I have not modeled the weight of wet concrete on the structure. I agree this is important. So you can consider the weight of wet concrete applied in this stage. And in the following stage, we have activated the members that represent the deck on top of the girders. And it is at this stage we'll remove the temporary supports in the beam and releases that were there to simulate the splice connection and the shoring members. And then the final stage is that where we'll be applying the superimposed dead loads on the structure and see the permanent condition of the bridge. So for this stage, we'll be monitoring the structure for over 10,000 days. All right, so let's take a look at the modeling process. So right now, looking at is a grillage model of twin girder system. If I click on the hidden button here, you can see that we have applied a part of the members to the bridge, but I have left one type of section for this demonstration purpose. So what I will be doing is going into tools, and we'll be using our special tool, which is called sectional property calculator. And here I'll be defining the unit systems I'm working in. And since the sections are pretty varied, I will be directly importing the section using a drawing file. So this is a section file that I'm importing, and here you can see it is just a DXF representation. It has a concrete tub, the lid member, and the deck on top. And now what we'll be doing is assigning the material properties to it and then computing its cross-section properties. So for this, we'll be first defining the material. We'll go to model, material, and I'll quickly click add here and define the material, let's say 1, and section name of the material is C9000 grade concrete. I'll enter the modulus of elasticity, which will be 4:6 ratio, and the density of the material, that will be in cubes per inch cube. And then I'll say apply, and since we have different material properties, we'll use different material here with a different modulus of elasticity. So that will be 3865, and percentage and weight density remains same. So I'll click OK here. So we have two materials defined. Now I'll quickly go to model, section, and then define a composite section and say generate. So I'll give it some name to begin with. I'll call it U girder, and this is the right side of the bridge. So I'll say R. It will have 3 parts. You can go up to like 1 or 2 or 3 parts. The base material is C9000, and I'll say apply. So just a section name has been defined. Now I'll add part to this composite section. So I'll say part 1. I'll call it Girder. I'll select plane. I'll select the material, and then I'll just select the geometry that defines this section. So I'll say this, press on the control button, and I'll click all the edges. So I have this member that will be the tub section. So I'll say apply. Then I'll add the second part to it, and I'll call it lid, and this material will be C45. Let me choose a different color, and I'll just select the boundaries, and I'll unselect the members that I don't need, and I'm just pressing the control button and clicking on the members to unselect it, and then I'll say apply. And then I'll define the third part of this section, and I'll call it deck, and the material property remains same, but let me use a different color so that you can notice the difference. And I just press the control button and quickly select the sections. And I don't want this section in there, sorry, so let me unselect it. I have to just select the boundary of the deck slab that is here, and I'll say apply. So I have defined these 3 sections with the material property, and all I need to do is just go to property and say calculate composite property. I'll give it a mesh size, let's say 1 unit, and I'll select the entire section and say apply. And now the program is computing its cross-sectional property. So internally, program is dividing this cross-section into a mesh of 1 inch by 1 inch, and computing its section properties. So once the color changes to normal from red, it means the properties are calculated, and you can read it right here. The properties of the composite section are calculated. Then you can go to property and go to composite property table, and then you can see this is a Girder. Its section properties are given here. Then lid, then deck, then Girder plus lid, and Girder plus lid plus deck. So once you have calculated the section properties, all you need to do is just go to properties, go to model, section, composite section, and just say export. And here I'll define it, give it some name. I'll say Girder dash R. Say I'll change this name to R1, and I'll say save. And now I'll just select the entire cross section and say apply. So now the section is created and saved, and all I need to do is go into the program here and go to properties, section properties, click add, and since it is a composite section, I'll go to composite tab, and I'll select composite general, and here I can import this section from where I just created. It's called Girder section right 1, and say open. So when the program brings in this section, it will bring in the section properties, and here the program asks you what part of the section is to be considered before composite action. So before composite is part 1, which is the Girder that we defined, and you can click on calculate section properties. You can see different section properties. You can define different parts as composite or non-composite, and then you can change the section offsets to match the profile if you want. So let's say I'm going for right bottom, and I'll say user defined and try to change so that it can match the alignment. with respect to the extreme fiber, my bad. So now you can see this is where I want to create the section from, and this blue dot is the centroid. So you can see they are fairly close, but just to be more accurate in applying it to the bridge here, I want to maintain the geometry by using the section offset. So I'll click OK here, and here I'll define it, let's say section ID 100, and give it some name, Girder -R, and I'll say OK. So now the section is created, and all I need to do is just select this undefined member here, or let me say unselect everything, go to a wireframe geometry, go to the top view, and just select the undefined geometry here. And when I turn on the hidden view, you can see if I just drag this section on the screen and drop it, you'll see the section is assigned to the members. So in this manner you can have the whole library of different types of cross sections, and you can just create the geometry, drag and drop it. Now I'll define the material property. So I'll go to the properties again, and here you can see time dependent material, where you can select creep and shrinkage, click add here, enter the name of the material property you want to define. You can select the code. We'll be using FIP 1990, and this concrete is 9 KSI grade concrete, and the notational size I'm defining it as 12. Now the program is intelligent enough to compute the notational size of each and every member of this composite section and analyze it. If you click on show results, you can see the graph, and then click apply, and I'll define one more for 4500 grade concrete, and it's 4.5. everything else remains same, so I'll just hit the OK button for now. So two material properties have been defined, and then I'll go into gain and compressive strength of the concrete. I'll say for 9000 grade concrete. Now here you must note that depending upon the code you choose, the definition of the strength changes. So if I use CBFIP, I have to enter mean compressive strength of the concrete, which is not the characteristic strength of the concrete. Mean compressive strength of the concrete is actually characteristic compressive strength plus delta F. This delta F is for the standard deviation, which is usually for concrete it is 1.166 KSI. So since we entered 9 KSI as the compressive strength, I'll add 1.16 to it, and the program will compute the total and apply it like this, and I'll say OK. Similarly, I'll define for 4500 grade concrete. I actually know this this is equal to 5.56, but just to show you this feature, I'm entering it right here, and then you can click OK here and close. And since we have defined two material properties, we'll be assigning this material property to the material grade that we are using, C9000, and associated with the grade C9000 material that we are using, and similarly for the 4500 grade concrete. And once you have defined all these material properties, I can move on and open another model file where I can show you what's next. So this is the second model file where we have defined the supports and the tendon properties. So let me quickly share it with you. So you can see the tendon properties that have been defined in this model. You can define pre-tension or post-tension strands. In this example, because I tried to replicate what was in the drawings, we skipped the pre-tensions, but you can consider pre-tension and post-tension together. And here you have to define all the curvature friction factors and wall friction factors. These factors are directly applied as per the equation that I showed you initially in the presentation for calculation of friction losses. And here you have to define the anchorage slip at the beginning and at the end. And also you have to define whether the tendons are bonded or unbonded. So once you have defined all this, it's very easy to define the properties. What I'll do is let me go to the top view, and using this select by polygon feature, let me quickly select one of the girders. So in this manner I can create a polygon of any side and select any profile, and then I'll say active. So now you're looking at just one girder. I'll check on the hidden view and let me right click and display the tendon profile. So here you're looking at, if I just scroll forward to zoom in, you're looking at tendons in the web. And if I go to the elevation view, you can see the tendons follow the pattern that were given in the drawing, on the standard drawings. And the nodes that you see here and here and here and here, they are the splice locations. All right, let me display it and activate the entire structure. Alright, so now here I'll show you how we define the temporary supports. So let me first show you where the temporary supports are located. To simulate the splice connections, we have applied beam and releases at these locations. So the beam and releases, if I just zoom in here, are applied to release the moments, because there are two ways of simulating it. Either you have a physical gap between these two elements because you don't want them to transfer any moment, or you can apply a beam and release that doesn't transfers the moment from one member to another. So therefore, to make the modeling relatively simpler, what we did is we used the beam and release at these members. And if you go into the definition of beam and releases, you can release the moment at I or the J end, or any type of force that you want at those splice locations. So in this case, if you read, we have released the moments in the member. So having done this, in this way you can model the splices, but this is not a part of your permanent structure, because at some point there will be no splices, there will not be any temporary supports, so they have to go. So therefore you have to construct this entire bridge using the construction staging, and then activate and deactivate these support conditions. So let me display the boundaries also. So these are the locations, as you can see, where the beam ends are applied, are the shoring locations where you will be applying your temporary supports. And these are the expansion bearings at the other ends, at the two abutments. And the interior piers are fixed. Like this. And so let me unhide this and quickly walk you through the construction sequence. So this is where we have defined the construction staging. The first stage, we have the girders and the support nodes applied. Under boundaries, we have just applied the links and the abutments. But what we'll be doing is we'll be applying beam and releases, bearings and temporary supports all together in the first stage only. So this is where you activate the boundaries, and loads you will see is just the self-weight applied. So we are sticking to the schedule. Okay. Alright, so because I had already activated the bearing at a later stage, therefore it was prompting me that I'm reactivating an already activated group. So program keeps a check on these types of human errors. Now what I'll do is select these boundary groups, add it here, and I want to add them as per the deformed locations, and then I'll say apply. So in the first stage we have applied the temporary supports. Then in the second stage we are doing nothing. We'll be using this stage to activate the lid part of the girder. And then the third stage is where we'll be applying the post tensioning. So you can see under loads we have applied the post tension. It is the stage where we'll be removing the temporary supports and the beam and release members. So we'll select them and put it under deactivation. So it is this simple that whenever you have to throw something in the analysis, you can just activate it. Whenever its role is completed, you want to remove it, you can just deactivate that particular load group, boundary group, or structure group. And then we'll move on to the fourth construction stage where the deck members are activated. You can see with their corresponding age. And the final stage is for 10,000 days, and the load or superimposed dead load is activated. So this way you can define the construction staging. And let me now show you how you capture the composite behavior. So this icon really helps in generating the or defining the composite section during construction staging. I've already defined the three other sections. Now I'll show you one that we brought in. So here, when I select the section as U girder R section, that is the section we just defined, you can see that they are highlighted on the screen. So this section is identified as a three-part section. So you can see there are three parts here. First section, material type is, or part 1 is material as 9000 grade concrete. Then the second, the third column is when you want to activate that part in the first construction stage, with age as 28 days of concrete. And this is the notational size of the member that is computed automatically by the program based on its cross-section details. By the way, for those who don't know what is the notational size, or they probably know it by another name, it's called volume to surface area ratio, or something similar to that. It is a different formula, and this terminology is taken from CBFIP code. If you need more details, feel free to ask me out in the question box, and we'll be talking about that in more detail at a later point. Then the second type, or the second part of this composite section is 4500 grade concrete, and this will be activated in stage 2. So first stage we were pouring, let's say, or we were bringing in the precast lids, and then we were placing it on top. So, and this lid has been cured for 14 days, and then it has been applied. And its cross-section area is different, so its notational size is different. This property affects your creep and shrinkage value as per different codes. And then the third part is also 4500 grade concrete, and this will be activated in fourth stage with a concrete maturity of 14 days. And then we can click OK here, and we are done with the composite section definition. Sometimes we have multiple sections, and it's not possible for us to compute or update as we go. So just to be on the safer side, you can always click update all H. This means the program will just once again will check the notational size for all the members and update it right here. Now, while we are talking about notational sizes, we haven't defined the notational size for the connecting members, and for that what we have to do is just click on the dummy material here that will select all the connecting members here, and we can go back to properties and select change property, and here we can select the code, and this is the formulation for computation of notation size, which is twice the cross-section area divided by the area in contact with the atmosphere, and the factor A is generally 0.5 for the standard sections. So we'll just say apply here, and the program will automatically compute the notation size for all these members and apply it to the model. Now once we have defined all this, we are ready to run the analysis and look at the results. So what I'll do is Let me pull out the results quickly. So this is the analyzed file, and let's quickly look at the results during construction stages. So this is the first construction stage, and I'll just go to the result tab on the top and click on forces beam diagrams, and you can look at the results at the last step due to summation loading. And if I say legend, you can see the values also. In the same time, you can see the units is inch kips. Let me change it to foot kips here. So you can see at splice locations the bridge is simply supported, and depending upon the construction methodology, you could have this as a cantilevered construction, so you can get negative moment over interior piers. Then if I switch to second construction stage, you will see the moments will go up because we have added more load on top of this, because we have applied the then in the third construction stage, you will see we have applied the post-tensioning strand, so it is giving you the secondary effects taken together. And the then we'll pour the deck on top, and see you will see the bending moment diagram is now coming back into the expected range or the kind of layout you want or you are familiar with. And then you can also see the time effects. Then we'll go to the final stage, and you will see the bending moment on the first day and on the last day, and these are the results for the same. So in this manner you can capture the time dependent behavior. Now interestingly, you can check the results for the entire composite section or just for the girder part, which is part 1. I'll say apply. So this is the bending moment supported by the girder alone. Then let's see the amount of supported by the lid members that are applied. Only few sections have the lid members. And part so the part 2 for other sections is the girder here, or is the deck, and part 3 is only available in the certain span. So you can see how the bending moment is shared by different parts of the composite section. But if you look at the overall picture as total composite section forces, you can use these forces to design your sections. And just to give you a better better visual appearance of this whole assembly, I'll go to the construction sequence once more. You see the first stage where everything is erected. Let me go to the first stage like this. You can see all the girders are erected, but there is no lid on top. And then we'll come to the second stage, and you'll see the lid is applied onto a certain part. And then we'll go to third construction stage where we'll do the post tensioning, and then fourth construction stage where the remaining part of the deck or deck slab is applied, and then the final construction stage. Also, let me show you the boundary changes that we applied. Let me display them onto the screen. So first stage, you see the supports at the splice locations. Second stage, we'll apply just the lid slab in the high torsion zones. Third stage, we have applied post tension, remove the temporary supports. The structure is continuous now, so you can see the support is only at the interior piers and the abutments. And the fourth stage, we have placed the deck on top. So that is all I wanted to cover today in the presentation. And I see there have been several questions asked back and forth, and our engineers have been answering these questions in a timely manner. If there is if there are some questions we can take up now. This I can continue for another 5 minutes. And we'd like to thank Summit Engineering for sharing a lot of information with us, and that really helped me through in putting this presentation together. So just as a side note, Summit Engineering is one of our prime users also. So thanks a lot, guys, for helping us out. So let me see some questions here. Wow, there's so many questions pouring in. Okay. Let me see. So, well, the engineer is asking, how does the program account for the negative moment in the deck over the pier? Is it a cracked section properties? Yes, we do have those features that can consider the cracked section behavior. You can define them and consider it. Otherwise, you can physically go in and control this section stiffness to account for these type of behavior. Alright, there another question that is coming in is, can you elaborate on the concept of a dummy deck and how the two girder lines are tied together? Yeah, the dummy deck is actually very similar to our regular grillage analysis. What we are doing here is, let me go to the hidden view so you can see the wireframe. So what we are doing here is we are modeling the cross section as a line element with its all the stiffness taken in the longitudinal direction, and these dummy beams are the members that are connecting the adjacent girders together to transfer the forces from one member to another. And the dimensions and the section stiffness properties of these dummy members are somewhat pretty standard. There are two ways that are very commonly used. The first way that we used here is, if I go right click and go into the properties, the deck is, this dummy deck has the thickness equal to the deck slab thickness, and the width is equal to the spacing that we are applying here. Now this spacing is a subjective issue. Engineers sometimes want to model it finer, they want, or sometimes they will go for widely spaced transverse members. Now finer the placement, better results you get in the transverse direction, and more closer it gets to the finite element layout. But once you go beyond beyond a certain limit of placing your transverse members, you will see that it will unnecessarily increase the runtime, and you will not be improving your results. So engineers perform usually try to monitor the bending moment force or bending moment distribution between the two girders by reducing the stiffness, and when they come to a point that the bending moment in individual girder is not reducing after a certain point, that means not being shared any longer with the adjacent girders, they come to this limit on the width. And so this is the standard practice. The another way of modeling these transverse members is calculating the stiffness in the transverse direction based on the section properties of the entire cross section. There is a really good book by Hamley that describes as how these cross section stiffnesses are computed, and you can apply that in the transverse direction. I hope that answers your question. Then another question that's coming in is how to define loads and trucks, HL93 trucks, as per standard codes. So in this particular software, we have a very neat way of defining these load cases. So once you go to load, you can see there are different types of loads that you can apply. The static loads, temperature loads or precessing loads, then moving loads, seismic loads, construction stage loads, heat of hydration loads, settlement or miscellaneous loads, and different load tables can be generated. So for static, for moving loads, all you need to do is just go into moving load, select a standard. Let me go to the pre-processing mode here, base stage. So here we have defined H2 LRFT, then you can define the traffic line lanes and traffic surfaces. So these are the two options that you can use to define the lanes. If you are using plate elements for your surface or deck, then you can use traffic surface lanes, which is predominantly for does the analysis as per influence surfaces, and then you define the vehicles. So when you go into vehicle, you can add standard. You will see all HL93 truck, tandem truck, fatigue truck applied. You can define a dynamic load allowance to it. If you want to define as per H2 standard vehicles, you can find that them also here. Then there are some special Caltrans load cases that are available. You can select their design vehicles. Then if you don't find the vehicles here, or you want to define your own DOT special vehicle, you can go to permit truck and you can define any kind of vehicle with any kind of wheel arrangement underneath it. So it's a very efficient tool that we first developed for Caltrans under the contract with AASHTO for performing major load rating projects. I hope that answers your question. Another question that is coming in, by the 28 days girder, do you mean the girder has been already cured for 28 days when it is being erected? Yes, that's true. The girder has already been cured for 28 days and then brought to the field. Now sometimes engineers want to let the rest of the curing to occur on this while the segment is already in place. So you can then define the age as 14 days and let the structure stay as it is for the first stage with the duration of 14. So that makes up for 28. I hope that answers your question. So I see okay, there's another question coming in. If you have a deck and the lid slab, why do you need the dummy element? I think this dummy element is a misnomer. I apologize, I should have used another name that is creating some sort of confusion. We call it dummy element because it is not really in the physical world that you can see. It is just to replicate the transfer stiffness of the deck. So when we are saying we have the lid slab and the deck slab in picture, we are saying that their longitudinal stiffness is taken care of, and the transverse stiffness of the deck is being represented by a transverse member. So that member is very essential. If dummy elements or the transverse member is not in place, then there is no way that one girder line is sharing load with the other girder line, unless you make this as a finite element model with the with the webs and deck slab, everything with plate elements. And for concrete bridges, I would not recommend you to use plate elements for webs and all, because there's hardly any out of plane bending occurring in concrete thick girders or concrete webs. They are not like steel plate girders where that phenomena is quite important. So if you are modeling a steel plate girder bridge or steel box girder bridge, then modeling everything with finite elements makes sense. And when you are doing that, then you will not be needing dummy elements, because then your deck will also be with plate elements. I hope that answers your question. There's a very good point made out here, that when you post tension, are the temporary supports restraining any vertical movement upwards or creating secondary effects? Yes, that's a very good effect. If our members are restrained by the temporary supports, and then the post tensioning is done, there will definitely be secondary effects in the structure, because it is at the end an indeterminate structure. So for that reason, what we do is, before doing the pre-tensioning, we always remove any temporary supports that are there. But if it is there in the picture, yes, it will have the secondary effects, and you will have to analyze it for the secondary effects at that stage. I hope that answers your question, Alex. How do you model a haunch or other variable cross-sectional properties? That is subjected to how you define or draw your cross-section. Remember when I showed you in the section property calculator? Let me just open that existing model here. I hope it is still here. In this section, you need not always have this member connected. You can leave a gap here and then model it on top. The program will consider that there is a haunch here, and the section properties will be calculated accordingly. Basically, it will just increase the distance from the centroid and increase the moment of inertia from the sections. And to consider the haunch, you can apply it as a, if you really want to consider its load and you want to be accurate in the dead load effects, then you can consider the weight of that haunch onto the structure as well. So in that manner, you can consider the variable cross-sectional properties due to the different haunch heights. So therefore, there is hard to find a platform or a spreadsheet that will consider all those variations. So the best thing that you can really do is make different DXF section drawings with different types of haunch heights that you are working with, and you can just throw that into the section property calculator. In one sheet you can fit in as many as sections you want, compute all the properties, and then throw it back into the software for running the analysis and doing a scenario analysis, I would say. I hope that answers your question, David. Great. Another question that is coming in. So can we use rigid links instead of dummy elements? Rigid links shouldn't be used because they are infinitely stiff, and if and what they really do is they transfer entire load from one source to another, which is not the true behavior of the deck, because at any given time the force is being transferred with the member whose thickness is this much only. So the section stiffness is overestimated if you use a rigid link to connect the two lines of the girders. So Abul, I would suggest you not to use rigid links. Instead, just use the dummy members instead with let's not call them dummy members, I'll call them transverse elements with these cross-sectional properties of the deck slab, or based on Hamley's equation you can, if you are working on several cell box girders, then that is very useful. Alright, so we have several questions coming in, and I don't want to hold everyone in, so what I'll do is we have the questions recorded with us in this chat window. We'll be contacting you guys individually and discussing further, so please don't hesitate. Here are our contact details. Feel free to call in at any time, and we'd like to hear your feedback about these sessions, and if you have any further questions and would like to discuss with us, do contact us at the given contact details. My name is Arun Sharma. The phone number is right here, and this is our open email address where you can where I'll receive all the questions that you have. So once again, this is Arun Sharma from Midas signing off from here. Have a great day ahead, and we look forward to hearing from you guys. Thank you.